Hypothesis testing with students' t-distribution. What if our interest involves testing to see if the population mean is greater than, less than, or just different than some value? We can use our t-score, y bar minus mu over s over the square root of n, as our test statistic instead of z. Now we're going to have to learn how to use table T or technology such as StatCrunch to find probability or p-values, or just bound them. Now the steps of a hypothesis test begin by defining your parameter, mu. Next, identify your null and alternative hypotheses, h sub 0 and h sub a. Then give your decision rule. Remember, your decision rule will always be stated in the form of reject the null hypothesis if the p-value is small enough and the value you compare against is the alpha or the level of significance. Then you would identify the form of your test statistic and calculate it using your sampled data. In this case, t is our test statistic, and it is calculated as y bar minus mu divided by s over the square root of n. Remember, in the numerator, the sample mean always comes first and the population mean always comes second. You may need to verify the method is valid, so you're looking for a random sample, sigma is unknown, and either the population you're drawing the sample from is normally distributed, but if not, then you need a sample size of at least 30. Then calculate your probability or p-value based on what you calculated for your t-score, the degrees of freedom, which tells you which distribution you're looking at, and the alternative hypothesis. Again, it's useful to draw pictures in this case. Then use table T or StatCrunch to get your actual value. Then make your decision. Just apply your decision rule. What are you going to do with the null hypothesis? Are you going to reject it or fail to reject it? And finally, summarize your results, including the level of significance, whether there was enough evidence to prove the alternative, and then a restatement of what the alternative hypothesis was. So let's look at a left tail test example. A local radio station claims that they play an average of 54 minutes of music every hour. A listener believes the statement is incorrect and wants to prove the station plays less than 54 minutes of music on average each hour. So the listener monitors 36 different 1-hour time slots and records the amount of time during each of those hours which the station played music. She finds the mean and standard deviation for those 36 observations to be 53.2 minutes and 2.1 minutes. Does this provide evidence the listener is correct? Test using a 0.05 level of significance. So we begin by saying the parameter mu represents the mean time spent playing music per hour among the population of all hours for this radio station. Under the null hypothesis, mu equals 54 minutes, and under the alternative, what the listener is trying to prove is that the population mean mu is less than 54 minutes. Since mu is less than 54 minutes, has a less than inequality, this is a left tail test. Values in the left tail of the t-distribution are going to support the alternative hypothesis. Next comes the decision rule. We reject h sub 0 if the p-value is less than or equal to the alpha level or the level of significance, which was 0.05. The test statistic t is the formula y bar minus mu over s over the square root of n. Now the sample mean was 53.2 minus 54 minutes if the null hypothesis is true, which states that mu equals 54 minutes. And in the denominator we have the sample standard deviation of 2.1 minutes divided by the square root of sample size, which was 36. This calculates out to be negative 0.8 divided by 0.35, and that is exact in the denominator, and that gives negative 2.29. Is it valid? Well, a random sample of times was taken. Sigma is unknown, so we're using the sample standard deviation S of 2.1 minutes, and n equal to 36 meets my at least 30 requirement. So yes, it would be valid. Now the p-value. The degrees of freedom is n minus 1, so that would be 36 minus 1, or 35. Now we want to know the proportion of t-scores which are less than, which matches the alternative hypothesis inequality, what we calculated, negative 2.29. Now you'll notice your table T, only gives you the area on the right of positive t-scores. It doesn't have any negative numbers in it. But because the curve is symmetric about 0, just like the z-curve, the area to the left of negative 2.29 is the same as the area to the right of positive 2.29. So in table T, we want to look across the row with 35 degrees of freedom. So I'm going to get out of PowerPoint and go into the table so we can see where these numbers are coming from. So with table T, notice the one-tail probabilities are just on the right because our t-scores are positive. So for the degrees of freedom of 35, we're in this particular row, and remember my t-score was what value? 2.29. So that's going to be trapped between these two values here. So if I go up to the top and look at the one-tail probabilities for these two columns, the one-tail probability is between 0.01 and 0.025. Okay, 0.01 and 0.025. Somewhere between those are going to be the probability or the p-value that I'm looking for. So now back into PowerPoint. Okay. So between those two numbers is where my t-score lies. So the one-tail probability tells me that the value, the part that I would shade sort of in red, is somewhere between 0.01 and 0.025. Now the more accurate p-value looks like it's around 0.0138, although let's go back and double check that because that might have been based on a different value. So we'll use the negative 2.29 and actually find the less than, and then this number may not be quite right, but we can change that. So now I'm going to go into StatCrunch and I'm going to use the calculator. So under Stat, there are these calculators which you can find probabilities with. So I'm going to go down to the T. I need the degrees of freedom to be 35, and I want the chance that my score is less than or equal to negative 2.29. Okay, and actually the reason this is incorrect is that I had rounded off and used like 2.3 before, but now I wrote it to 2 digits. So, but it's really close. It's 0.0141 if I round that off, and that would match exactly how I would want to draw the picture. Now what I did was, using table T, I found the area to the right of positive 2.29 and just recognized that it is symmetric. So it's still the 0.0141. So let's go back into PowerPoint now. And I can change this 0141. So the p-value I know either from the table is between 0.01 and 0.25, or I know it's about 0.0141. Either way, I know it's less than 0.05 because any number between these two has to be less than 0.05. So my decision is to reject the null hypothesis, which means in summary, I would say using a 0.05 level of significance, there is evidence. I do have significant evidence to conclude what the mean mu, right? The mean time per hour this station plays music across all hours really is less than 54 minutes. So it seems that the listener was correct in her assumption. Let's look at another example. This is a two-tailed test. Okay, now with the two-tailed test, I'm going to be able to look up or bound my t-score because I want to go to the right of the positive value and to the left of the negative value. Remember what a two-tailed test looks like. Suppose that ball bearings manufactured by a company have to be 1/2 inch in diameter. If they're too small, they may fall out or don't support enough weight. If they're too large, they don't roll around the housing or the case that they're in correctly. Either situation is bad. The company wants to see if there's evidence that the lot or the production where they produce probably thousands of these. This lot that they produced last week has a mean diameter that differs from this 1/2 inch target. A random sample of 46 of these balls are measured and they yield a mean of 0.494 inch and a standard deviation of 0.03 inch. Perform the test using a 0.01 level of significance. So the parameter mu is the mean diameter in inches for all balls produced in the lot. Under the null, we're saying the mean is 1/2 inch. Under the alternative, we're looking for mu to be different than 1/2 inch, and that could mean it's smaller or it's larger. The decision rule says to reject the null hypothesis h sub 0 if the p-value is less than or equal to 0.01. The t-score is y bar minus mu over s over the square root of n. So then we look at our sample data, and the sample mean is 0.494 minus what the null hypothesis says mu is, 0.5. Then in the denominator, we have 0.03 divided by 0.46, which is 0.004423. That gives me a score of negative 1.36. It's valid since a random sample of diameters was taken, sigma is unknown, so we're using the sample standard deviation of 0.03, and n equal to 46 is at least 30. Now for the p-value, notice the alternative hypothesis is not equal to, so this is a two-tailed test. We want the area to the left of t equal to negative 1.36, so that's the left side, plus the area to the right of t equal to positive 1.36. So what we're finding is the probability a sample is 6/1000ths of an inch. Okay, 0.494 minus 0.5 was 0.006. So 0.006 inches or more away from 1/2 in either direction, either below it or above it by at least that much, if mu is really 1/2 inch. So we need the degrees of freedom, which is n minus 1. So 46 minus 1 is 45. So we would use the degree of freedom equal to 45 rho. And what I want are the two values of t-scores, which are a little bit less than the 1.36 and a little bit more than the 1.36. Let me go to the table. So for 45 degrees of freedom, I want to bound 1.36. Well, it's going to be between 1.301 and 1.679. Now remember, I've got the two-tail probabilities at the top of the column. So the 1.301 tells me 0.20 would be the part in red, and the 1.679 says 0.10 would be the part in red, or the two-tail probability. So I know the p-value I want for a t-score of 1.36 or negative 1.36 is somewhere between those two numbers, 0.10 and 0.20. Now if we did this, okay, so I'm going to go back to PowerPoint for just a minute. Remember, we're doing a two-tailed test. My t-score is 1.36 and negative 1.36. So I want to bound how much is outside of those for 45 degrees of freedom. So I can go into StatCrunch and do a calculation and get that. Now to do this, I'm going to do the between. It's going to tell me how much is between the t-scores, so I'm going to have to subtract to get how much is in the two tails. But for 45 degrees of freedom, okay, so if we go back, remember 1.36 is my t-score, 45 degrees of freedom, okay, then click compute. What's in red is this part. Okay, so what is in white is what I really want. So I take all the area, which is 1, minus what's in red. So 1 minus this would be about 0.8194. So 1 minus that would be 0.1806. So 0.1806 is the actual, more accurate probability. Notice in PowerPoint though, let's go back here, that the only thing I can do is say it's between 0.10 and 0.20 using a table, okay, but that's still good enough for me to make my decision. So the exact p-value is somewhere between those, or we calculated it out, but either way that's enough to make my decision and write my summary. So the p-value being between 0.10 and 0.20 means my decision is to fail to reject the null hypothesis. It's not small enough, right? It's not less than that 0.01. Now think about what the p-value is measuring, okay? What the p-value is measuring is if the population mean diameter really is half an inch, the 0.5 value that the null hypothesis says, then the chance I get a sample mean like I got for the 45 balls that were measured, which is 0.494, which was 0.006 inches, and then the chance that it's either that much below or above, okay, that half an inch target, the chance that would just happen if the true mean of the entire lot of however many thousands were produced really is half an inch, the chance of being 6/1000ths of an inch or more below or above half an inch would be somewhere between basically 10% and 20%, or between 1 in 10 and 1 in 5 samples. So what happens is this isn't very unusual to see if my population mean, the mean for all of the balls in the lot, is half an inch, then this wouldn't be unusual to see at all. Okay, so it doesn't make me doubt that the mean really is half an inch. So at a 0.01 level of significance, there's not enough evidence, okay, there's insufficient evidence to conclude that the mean diameter for the entire population, all the ball bearings in the lot, differs from half an inch.